Alright, in this video, I'm gonna go over the seasonal AR/MA model and then go over the ARMA model. In its name, you can kind of see that it combines the AR and MA model, and that's basically what it is. But before that, I'm gonna go over what the seasonal AR and MA model is. The seasonal AR/MA model, we could abbreviate as the S-AR or MA, is if you recall the seasonal component of the analyzing time series, so kind of the seasonal patterns of what we observed of quarterly, monthly, and daily. We want to mathematically kind of show how we could show that. Remember, we call it seasonal dummy variables that we went over. And so, if we're going by like a regression equation in our seasonal model, we can show that in this AR model, there's a coefficient and the y variable. This is represented by a lag of 1. But then for monthly, we can write like a times 12 to show that this is a monthly coefficient and variable. So the order of this model to the right is lag of 1, but the seasonal S equals 12 to represent monthly. Likewise, we can write two variables, one with the lag of 1, one with the lag of 2. And then we want to be consistent, so still write in times of 12. Should this be 24? I'm not sure. I'm not exactly sure if this should be 20. Actually, I do think this should be 24, so that's an error on my part. But so 12, 24. So each time unit is represented by 12 months. And so for the ACF and PACF, you'll see a similar pattern to what we saw, but because each time unit is represented by 4 months or one spike, there's a spike within every quarter. This is an example for quarter. This we did for season. So now we're switching up to 4 months. But every 4 months, there's going to be a spike in the ACF and then one spike for the PACF if it's a seasonal AR1. All right, seasonal MA2. Let's try that. Seasonal MA2 for monthly, and so if we're using monthly, then that's every 12 months because there's a spike within a single month within every 12. And so for a moving average model, there's a gradual decrease in the PACF, but then a spike in the ACF, and then zero everything else in every all the lags after. And so for a seasonal MA2 model, we have 2 spikes. Because it's monthly, we have every 12 months, spikes at every 12 months. So 12 and 24, and then a gradual oscillating decrease at the PACF because it's an MA model. If it's an AR model, then gradual decrease at the ACF, and then 2 spikes at the PACF. Not much different from what we already went over. Just, we have to pay attention that it's actually seasonal. All right, now moving on to the ARMA model. So, like I said, the ARMA model combines dynamics of the AR and MA model. So, remember the AR model gives analysis based on past errors, and the MA model does that based on the errors. AR model is based on the past values. And so what the ARMA model will do is use a little bit of both to what we call achieve parsimony and parameterization, a fancy way of calculating the coefficients. So in the ARMA model, we can see that we have both the AR here and the MA here. So one error here and one past value here of y. Algebraically, this is like another fancy way of writing phi and then theta, but it's just in different symbols because, as you can see here, if this part is stationarity, then we can model it as this part, and then in invertibility, we can kind of switch the coefficients around, and then this is what it will represent. This is in terms of the error, this is in terms of the y. So algebraically, there's a lot of flipping and back and forth, but conceptually, it's pretty simple. ARMA model utilizes both AR and MA. As you can see here, this is the AR, this is the MA, that uses the error. The AR uses the lagged value of y. And remember that it needs to be both stationary and invertible. So yeah, I think invertible is both for the AR and MA. I'm not sure if stationarity is, I think stationarity is only a requirement for the MA, not the AR. I could check on that later forward, but all right, last part is kind of the whole point of why we're using an ARMA. If we get results of the ACF and PACF kind of like this, where we're not exactly sure if we should use the AR or MA model. You know, there are like spikes here, but then there's also spikes afterwards. Same with the ACF. You know, maybe we sense a gradual decrease, but we're not sure. Then we'll use the ARMA model, and there is a formal test for it. In R, we can call, you know, auto.arima, and it'll show us the ideal model. But this is visually if we have to, you know, if we can't use a formal test, then circumstances like this is when we're going to use an ARIMA model, or sorry, ARMA model. And just know that more simple models that use less lag order are preferred. So in this case, an ARMA 2.1 is preferred over an autoregressive 4 because we're using 2 lags in the AR and 1 lag of MA opposed to 4 lags of AR. So kind of like add these up and then see if it's less than the MA. If it was like an MA2, then we would prefer an MA2 over an ARMA 1.3. Comparing even the same models, we'll prefer 1 lag order of the AR and MA composed of 2 lags of an AR and MA. All right, I think that makes a lot of sense. All right, that's going to be it for the seasonal AR, MA, and the ARMA model. I actually don't know what I'm going to do for the next video. I might go into regressional forecasting. I might go more into the ARMA and ARIMA model, which I haven't talked about that yet, but we'll see for now. But we'll see later, but for now, that's pretty much it for the ARMA model. Again, if we want to do formal testing, we can just do auto.arima and then get the results in the software in R. I'm sure it works in like Python and Stata too, but the whole point is that software is a lot faster. Yeah.